Do, 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 do. All right, well, I will, everybody's here. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and this time we have to meet and study your creation. Just pray again that you would be glorified in what we do and that we all understand a little bit more about adjoints and orthogonal transformations, all these things. Lord, in your name I pray, Lord Jesus. Amen. So this is the tail end of section 6.4. So this is, I think, the theorem I may have already proved this one, but I'll mention it again. Wrong one. So we have T, a linear transformation on a finite dimensional complex inner product space. Then T is normal if and only if there exists an orthonormal basis of eigenvectors for T. The proof basically is use Schur's theorem that gives you an orthonormal basis for which the matrix is upper triangular, which then means that the first vector has to be an eigenvector, because if you think about how a triangular matrix looks, that makes the first vector in the basis of eigenvector. And then we suppose by induction that it's going to be the case that we have, k minus 1 eigenvectors. And then if you look at the given upper triangularity, then you're able to prove that the kth one is also an eigenvector, because everything here you can show is 0 except for the AKK term, which ends up making AKK the eigenvalue for VK as well, for what it's worth. And there I'm using the orthonormality of the basis, which is given to us by Schur's theorem. So yeah, that's one direction. Then the other direction, of course, is just a calculation, pretty much. I mean, you've got an orthonormal basis of eigenvectors. That means that your matrix is basically the identity matrix with scalars multiplying, with different scalars on different components, but fine. If you multiply, the adjoint times A, you're just going to get the product of the eigenvalues and their conjugates in each of the diagonals, and they match up. And so diagonal equals diagonal, and each diagonal entry is equal, and they're just the magnitude of the eigenvalues squared in each diagonal, if you think about that. All right, so there you go. Just to reiterate, transformation on a complex inner product space is orthonormally diagonalizable if and only if it's a normal transformation, right? Where normal, remember, means that T star T is equal to TT star, right? Okay, so then an example of this, it's kind of interesting. The book keeps going back to this one example as its token infinite dimensional example, so it's nice. So the set of continuous complex valued functions on the interval 0 to 2 pi, there's the definition of the inner product, remember? And we have before talked about these guys as being an interesting basis. An interesting set, I probably shouldn't say basis, but an interesting set of linearly independent vectors, all right? They're orthonormal with respect to this inner product. And so he defines a T and a U operator by just saying, well, what I'm going to do is T of F is F1 times F, and U of F is F minus 1 times F. And so what that does in terms of this orthonormal set is just a shift. It goes to the next one, or it goes to the one before in the list, And if you calculate, you can do this. So this is that. And this is the kind of sneaky step right here. This is super sneaky step right here. Delta m plus 1, right, is equal to delta m comma n minus 1. Do you see that? So the only way this can be equal is if m plus 1 equals to n. The only way this can be equal is if m is equal to n minus 1. But that's the same solution set, right? So these are both 0 and both 1 on the same choices of m and n, so they're equal. But that's kind of cool, because then this we can trade for that inner product, which then is the u acting on Fn. So we've shown that if you take T, start out here, and move it over there, that's what happens. And since this is true on a basis, it implies that u is equal to T star, because you can extend this result linearly off the basis. So what that then means is that well, that's not immediately yet, but then it's pretty easy to see that t times t star is equal to t star times t, which is equal to the identity, right? Because notice that t and u are just undoing each other's work, you know? They're inverses. And so therefore, t is normal. So this is an example of a normal transformation on a infinite dimensional complex product. So the point of this example is to show you that the finite dimensionality matters, right? So the theorem I just proved, or at least sketched the proof of, it stated that if you have a normal transformation on a finite dimensional complex inner product space, it's orthonormally diagonalizable. So not only do there exist eigenvectors, there exists a basis of orthonormal eigenvectors. This thing is normal, but you can prove that it has no eigenvectors. All right? So you can look in the book, page 369 and 370, there's the proof right there that, in fact, this transformation has no eigenvectors. If you try to solve the eigenvector equation, you get nothing. So, much like the rotation in the plane. So, definition. A transformation is said to be self-adjoint if t star is equal to t, or it's also sometimes called Hermitian. And likewise, a real n by n matrix is self-adjoint if a star is equal to a. And the theorem we get. So notice that in the real category, self-adjoint just means it's symmetric for the matrix, right? So here's a lemma. If we have t as a self-adjoint linear operator on a finite dimensional inner product space V, then every eigenvalue of t is real. And if we have a real inner product space, then the characteristic polynomial of such a t splits. The proof of A is pretty easy. Check it out. So we have tx equal lambda x for x not equal to 0. We are given that t star is equal to t, right? Because it's self-adjoint, right? So t star is equal to tt is equal to tt star. So t is normal, right? And since it's normal, that means that it shares eigenvectors. We proved that last class, I think. Anyway, recently. So lambda x is t star x, which is, by the way, equal to lambda bar x. And since these are equal, that means lambda is equal to lambda bar, which is to say that the eigenvalue is real. So a self-adjoint linear operator has real eigenvalues. And proving that it splits, here's a proof of that. If we have an n-dimensional vector space in orthonormal basis, we can let A be the matrix of T with respect to said basis. Then the adjoint of A is the adjoint of the matrix of T, which is, by the way, the matrix of the adjoint. Remember that? But if self-adjoint, so the matrix, the adjoint is equal to T, right? And then that's A. So we have A star is equal to A. So A is self-adjoint. And if we were to define left multiplication by A on n, on Cn, then that would be a self-adjoint operator. Therefore, the eigenvalues are real, and by the fundamental theorem of algebra, the characteristic polynomial of A splits into factors of the form t minus lambda, and lambda is real, which means that, likewise, if we view A instead as a matrix over the reals rather than the complexes, we have that the characteristic of A split all over R. So, therefore, if the characteristic polynomial for A splits, the corresponding characteristic polynomial for the linear transformation splits. We always have this back and forth between the matrix and the transformation's characteristic polynomials. They are one and the same. So this is the big theorem at the end of section 6.4, which is that if T is a linear operator on a finite dimensional real inner product space, then T is self-adjoint if and only if there exists an orthonormal basis of eigenvectors for T. And here's the proof, at least the forward implication of the proof. Suppose T is self-adjoint. By the lemma we just had, the characteristic polynomial split over R, which ensures theorem applies, so we obtain an orthonormal basis, beta, for which this matrix is upper triangular. So we have A star is equal to that, which is equal to that, which is equal to that, which is equal to that. But both A star and A are both upper triangular. But remember what A star is, it's the conjugate transpose, right? I think in this context it's just the transpose, right? Because we're in the real case. So I'm following the book. He always writes stars where he could write transposes. It kind of bothers me, but I'm just sticking with it because that's his style, and it kind of bothers me a little bit because I'd really rather write a transpose when I can write that because it's more. But he's writing star so that you gain a better appreciation for the theory as a whole, the whole abstraction of treating both the real and the complex case at once. That's the reason it's being done. So I'm torn a little bit with the practice, but anyway. So if you have a matrix and is equal to it's A and A star, they're both upper triangular. The only way that can happen is if A is a diagonal matrix, right? Because if you have an upper triangular matrix which is equal to its transpose, think about it. That would flip everything that was non-zero above the diagonal below the diagonal in the transpose. So the only way that could be equal is if the only thing that's non-zero is on the diagonal itself. Which then means, of course, that beta is in fact an eigenbasis for T. So, and the other direction is left as an exercise. Don't worry, that's an empty threat, I think. So that's section 6.4. Now, I could try to write things out today, but I know better because you guys already broke my brain in office hours today, so I'm not going to try such a thing. Oh, by the way, we found a way easier way to do that problem later. Yeah, sorry about that. And I say we, I mean one of you guys. But so section 6.5, unitary and orthogonal operators. This word is mine, isometry. These are examples of linear isometries. Isometry means same measure. And so what's going on here is if you have a linear transformation in a finite dimensional inner product space, if the norm of T of x is equal to the norm of x, in other words, the length of T of x is equal to the length of x for all x, then T is in isometry. In particular, if f is equal to the complexes, it's called a unitary operator. If f is equal to the reals, it's called an orthogonal operator. All right. In the infinite dimensional case, T onto has to be added as a consideration. If you have that in addition, then you can call it a unitary or orthogonal operator if it maintains the length. But we need to add on the condition of surjective. I think there's a homework problem you guys have worked out that implies that this implies injectivity, but we do want our orthogonal operators to be surjective. So anyway. So here's an example of such a thing in infinite dimensions. Again, this favorite example of the book. he gets so much mileage out of this example. So suppose you pick a complex function which has modulus 1, its length is 1, all right, for each x. Then if we define a linear transformation tf equal to hf, first of all, is that a linear transformation? I didn't prove it, but is it clear? If you put in f plus g, you get h times f plus g, which would be hf plus hg, right? If I put a constant here, it pulls out. So yeah, it's pretty clearly a linear transformation. And if you calculate the length of T of f squared, right, that would be this squared, which would be this in terms of the, this is how we define the norm, right? The inner product of the vector with itself. And as such, we get h with h bar, which is the length of h squared, and then f with f bar, or f conjugate if you like. But this is given to be 1. Uh-oh. This is given to be 1, and, well, lo and behold, we're back to the length of f squared. So that transformation preserves the length squared of the vector, which means it preserves the length. Therefore, it's unitary. But is it? Because in order to know it's unitary, we would need to know what? It was surjective. Is it clear that this map is surjective? If you pick f and h, how do you map to it? I want T of something equals to, h times the something is equal to f, right? So what do I do? And why can I do that? Well, what do you, I mean, you say H inverse. I like that, but what do you mean by that? In what sense inverse? I agree with you, but what do you mean by inverse? Like additive, multiplicative, function? What kind of inverse?
I guess I was thinking
Well, no, easier than that. It's just like, you just do f divided by h as a function. That's a reasonable thing to do because what do we have? The absolute value of h of x is equal to what? 1. So does it have 0 as a value? Nope, it does not. So I can divide by h. And then, of course, this outputs f over h, which is equal to f. Check. Therefore, it is a surjection. So I can conclude, yeah, okay, it's in a unitary. This is, in fact, indeed a unitary operator on h. Yeah?
Did you really transform it? Did you just multiply by 1? Or is there a difference?
I'm not saying h is equal to 1. Just the length of h is equal to 1 as a complex function. So it's a multiplication by like a phase factor. Yeah. And that phase factor depends on x. So it could be a lot of things. Like this example could be a lot of different things. All right. So there are a bunch of different ways to characterize a linear isometry of the inner product. These are all equivalent. The last one, I think, is the actual definition that we gave. If t star t is the identity, if tt star is the identity, I like this one, it literally preserves the inner product. T of x with t of y is xy, like that, for all xy. D and E kind of look the same, but they're different if you study them. If beta is orthonormal, then the image under T is also orthonormal basis for V. On the other hand, there exists an orthonormal basis beta for V such that T of beta is orthonormal basis for V. And then F, which was our definition of linear isometry, right? That the length is preserved. These are equivalent. You can prove that these imply each other. All right? Don't worry, I'm not going to. Although I'm sure, sorry, but it is in the book, page 377 to 378, and it would easily eat an hour of our time. Yeah. And it's not really the point here. I want to get to the point, so let's go on. So any one of those is a reasonable characterization of what it means to be a unitary or an orthogonal operator, all right? So a corollary to that theorem is that if we have a linear transformation on a finite dimensional inner product space over the reals, then V has an orthonormal basis of eigenvectors for T with eigenvalues lambda j, such that the absolute value of the eigenvalues are 1, if and only if T is both self-adjoint and orthogonal. All right. So self-adjoint gets you the existence of an orthonormal basis by the previous section. Orthogonal says that the eigenvalues all have absolute value 1. That was not part of the previous section. That's new. Here's the proof. If we have forward direction, so we're going to assume we have an orthonormal basis of eigenvectors with absolute value 1, right? So suppose we have the eigenvectors, they're orthonormal, the absolute value is 1, let beta be the basis, the eigenbasis. Notice that the matrix is diagonal, right? The matrix is diagonal with the eigenvalues on the diagonal, and that's equal to the transpose, which is equal to the adjoint, if you like. So therefore, the matrix is self-adjoint. Of course, okay, anyway, the matrix is self-adjoint. Therefore, T is equal to T star. Furthermore, so that was part of it. We wanted to show a self-adjoint. We did that. And orthogonal. To see it's orthogonal, notice that T star T acting on VI is T star acting on lambda IV. but then t star is equal to t, so when that acts on vi, you get another lambda I, you get lambda I squared acting on vi. So that shows you that lambda I squared must be equal to 1, which then implies that the absolute value of lambda j is equal to 1. Oh, wait a minute. Sorry, we knew that. I'm using that here, aren't I? Sorry, I'll get my story together here. Let's work on the forward direction before we work on the reverse direction. Let's not do both at the same time. So we're assuming this, so that's why this is equal to 1, which then shows you that t star t acting on vi is equal to vi for every basis element. But then that implies that t star t is equal to the identity, which in the previous theorem was one of the equivalent conditions for orthogonality. So that's that. The other direction, suppose we have t is self-adjoint and orthogonal, then there exists an orthonormal eigenbasis by section 6.4, and since t is orthogonal, we have this step right here. So notice that the absolute value of the eigenvalue times that is equal to the length of the eigenvalue times vj, but if that's the eigenvector, then we have that's t of vj, but then again by the orthogonality, we have that the length of t of v is equal to v length of vj, and lo and behold, we get that the absolute value of the eigenvector is 1. Okay. Corollary 2 here. If you have a linear transformation on a complex inner product space, and you have, then V has a orthonormal basis of eigenvectors of t with, this is complex length of the eigenvalue being 1, if and only if t is unitary. So, yeah. And the proof of that would be similar to the one I just gave you, but we won't go through it. So I do have some specific things that you're going to need for a couple of the homework problems. Oh, homework problems. Yes, lest I forget. I got stuff. So I know you guys are lost without my homework. So here's the next one. So you take one and hand it back. So if you look in here, well, I guess you can't see from my, maybe, oh, see, now I don't have one. I meant to steal that from you. I'll give it back though. Let's see here. So I'm talking about number 84 and yeah, just number 84 pretty much is going to be partly based on what I'm about to show you. All right. So that's the one I'm thinking of, 84. We're not there yet though. Okay. So one thing at a time. So if we have a rotation by angle between 0 and pi, it's geometrically obvious, right, that the length of the vector, if you rotate it, is not changed, right? So the length of t of x is equal to length of x. Therefore, it's an orthogonal transformation, right? I didn't shoot you guys, and I stopped lasering when I went back like this, right? Like that, like that. Sorry, I should stop. Anyway, so of course the matrix of the rotation is this, and you notice it's not symmetric, right? Which is to say that if the matrix is not self-adjoint, then the transformation is not self-adjoint. Indeed, this, we already know there is no eigenbasis for this, right? It is not diagonalizable over the reals. However, if we were to complexify this transformation, it is complex diagonalizable, right? And in fact, this is a normal transformation. The complexification of it is anyway. Well, I mean, this is also a normal, I think this is also normal in the real case because, well, let me shut up. Let's see here. So this is new. Let L be a one-dimensional subspace, also known as a line through the origin. All right, a line through the origin is a one-dimensional subspace of the plane. A linear operator T is called a reflection of the plane about L if T of x is equal to x for all x in the line, and T of x is minus x for all x in the perp to the line. So if you think about the way that works, it just takes whatever's off the line and flips it over, right? So it reflects over the line. This is the definition of a reflection. So, sorry. So if we have a reflection of R2 about the line through the origin, suppose V1 is an element of L and V2 is in the perp to L. such that these are both unit vectors, all right? Then T of V1 is V1, and T of V2 is minus V2. So we have eigenvalue 1, eigenvalue minus 2. So what do we got? We've got an orthonormal eigenbasis for T, where the absolute value of all the eigenvalues is 1. Therefore, by corollary 1, T is orthogonal. So a reflection is an orthogonal transformation. All right? That's actually not how I typically look at orthogonal transformations. Truth be told, I almost always look at orthogonality in terms of what we're about to talk about right here. A matrix. A is orthogonal if A transpose A is equal to A transpose is equal to the identity. A matrix in the complex case is unitary if U star U is equal to U star is equal to I, right? Unitary matrix, orthogonal matrix. So ON is the set of all orthogonal n by n matrices. This is the set of unitary matrices, all n by n unitary matrices. Notice that if we had this condition, right? If A is concatenated, you know, the concatenation of the basis, let's say V1 through Vn, or vectors V1 through En, maybe you don't know their basis to start with. We'll check what happens. If V are the column, if these are the columns of an orthogonal matrix, A transpose A is equal to I is equivalent to Vi transpose times Vj is equal to Kronecker delta Ij. If you look at just the matrix product here, the row column rule, the usual dot product of rows and columns, gives you that. But of course that's the inner product in our context, or if you like dot product notation, whatever. The point is that the columns of A are orthonormal. And this goes both ways. Given an orthonormal basis, if you concatenate those vectors, you get an orthogonal matrix. Conversely, if you have an orthogonal matrix and you take column by column, right, column by column, the vectors that form the matrix, that will give you an orthonormal basis. Not orthogonal. Well, I mean, technically orthonormal is orthogonal, right? But be careful, if I give you an orthogonal set of vectors and you concatenate them, that doesn't have to be an orthogonal matrix. Because the normality is important. You need the unit vectors. So if I just take orthogonal vectors and I put them together in a matrix, I don't have any guarantee that I get 1 when I take the dot product of the vector with itself, right? So you have to have a normalized basis for this to work. And yet we don't call it an orthonormal matrix, you know? We call it an orthogonal matrix. It's what it is. So proposition, if you have an orthogonal transformation on a real inner product space, finite dimension, if and only if there exists an orthonormal basis for which your matrix for T is an orthogonal matrix. Likewise, T is unitary on a complex inner product space, if and only if there exists an orthonormal basis for which the matrix of said transformation is unitary. All right, so there's a one-to-one correspondence between orthogonal matrices and orthogonal transformations, between unitary matrices and unitary transformations. That's how it goes. And if we go back and we look at our previous example, it's easy to see. Like example 3 revisited, we had beta basis V1, V2, you know, the matrix was 1, 0, 0, minus 1. That is clearly a orthogonal matrix. I say there's 2 ways you could see this. What are the 2 ways? The 2 ways, the one way is just simply to calculate this matrix transpose times itself, and you'll get the identity matrix. Because when you multiply diagonal matrices, you multiply the diagonals. So 1 times 1 is 1, and minus 1 times minus 1 is minus 1. 1 is 1. Let's try that again. On the other hand, if I look at the columns, they form a orthonormal set, right? Orthonormal set. Now, example 4, you have a rotation, has the standard matrix cosine sine minus sine cosine. Check this out. This vector and that vector, perpendicular. They're both unit vectors because sine squared plus cosine squared is 1, right? So this is a clearly, columns are clearly orthogonal and length 1. That's the columns form an orthonormal basis for R2, therefore this is a orthogonal matrix. Conversely, you could just check that this matrix times its transpose gives you back the identity. Also true. You could check that, okay? So rotation is an orthogonal transformation. Example 5, a little bit more interesting. Suppose we have a reflection about a line L through the origin, and let beta be the usual standard basis. And so this is I usually just use bracket t equal to a. I don't know, like the book is doing all this fancy schmancy stuff, but whatever. So t is left multiplication by a, right? And since we previously argued in example 3 that t is orthogonal, it means that a must be a orthogonal matrix. The matrix of transformation, the matrix of an orthogonal transformation must be orthogonal. So here's the line that we're reflecting over. So first of all, we'll say we're going to characterize it by the angle, positive angle off the x-axis, all right? So suppose the line is at angle alpha in this sense. Then v1 is a vector along L, cosine alpha, sine alpha, right? That's an element of L. If I flip these and put a minus on the first one, that is perpendicular, right? This dot that is 0. Therefore, v2 is in the perp to L. Okay? And they're both length 1 because they're clearly length 1. So gamma, v1, v2 is an orthonormal basis of R2. And we have, by definition of reflection, t of v1 is v1, t of v2 is minus v2. Remember, this is the definition of reflection. It flips things in the perp, and it leaves things that are collinear alone. This is the reflection definition. That serves to define it, right? Because we know in 2 dimensions that L direct sum with L perp is everything. I mean, that's always true, isn't it? W plus W perp is always everything. You know? But, okay, so, look at that. Then the matrix of T with respect to this gamma basis is simply 1, 0, 0, minus 1. But we also know coordinate change. Remember? And so the matrix with respect to a non-standard basis is the non-standard basis inverted times the standard basis times the standard matrix rather, times the standard basis times the non-standard matrix again. I can solve that for A, right? A is matrix of gamma 1, 0, 0, minus 1, matrix of gamma inverse, but this is the gamma and that's the gamma inverse. Now, how do I know that the inverse is just that? Can you guys tell me? What's the inverse of a rotation by alpha? This is a rotation by alpha, by the way. Rotation by minus alpha. So we have cosine minus alpha, also known as cosine alpha, and sine of minus alpha pulls out the minus. So you just have to flip the signs for the inverse. So this is indeed the inverse matrix to that. And then you multiply it out, and you get sine squareds and cosine squareds and such, like this, and that, and that, and that. And this is cosine 2 alpha, and that is sine 2 alpha. And there you go. So what this is what the matrix of a reflection about a line through the origin at angle L. This is the formula for the reflection matrix. So that's the point of this example, is to derive this formula as a point of reference, right? While we're at this, what's the determinant? What would be the determinant of this matrix? Minus 1, right? And so this is what we're going to learn, is that rotations have determinant 1, whereas reflections have determinant minus 1. All right? I'll talk a little bit more about that once I put the projector away here, but an orthogonally equivalent, A is orthogonally equivalent to B if it's similar, if there's a similarity transformation from A to B by an orthogonal matrix. So if there exists an orthogonal matrix P for which P inverse AP is equal to B. Likewise, A is unitarily equivalent to B if and only if there exists a unitary matrix P for which B is P inverse AP. All right. Of course, you can make these P inverses into what? P star, right? Because since, you know, P star P equals to I equal to PP star means that P star is the inverse. So in the real category, that's a transpose. In the complex case, that's the you know, conjugate transpose, gives you the inverse. So what this all means, two takeaway messages here. A complex matrix is normal if and only if A is unitarily equivalent to a diagonal matrix. So that means that we can choose a coordinate system that will similarity transform A into a diagonal matrix. All right. And likewise, A is symmetric if and only if A is orthogonally equivalent to a diagonal matrix. So that means I can multiply, I can sandwich A between an orthogonal matrix transpose and an orthogonal matrix and change from a complicated formula for A into just a diagonal formula. We'll see what that means for us in a minute. This I'm just sharing with you as a point of trivia. When I teach abstract algebra, I take a day to prove this. All right, this is subtle. This is really subtle. But a rigid motion is a function which preserves the distance between points. See this? So like this is the distance between x and y. Excuse me, this is the distance between f of x and f of y. This is the distance between x and y. All right? So a rigid motion is something that preserves the distances between points. It has the idea of like, imagine you feed space into some function and it maintains the shape of things. That's the notion of the rigidity of the motion. So like if the distance between all points is maintained, the idea is that you're not going to be squashing shapes or something, right? If you're squishing a shape under the transformation, the distance between 2 points might not stay the same. So it's not too far of a leap to say, well, if the distances are maintained between all possible points in the shape, that should be maybe what we call a rigid motion. Something that takes cubes to cubes and disks to disks and SpongeBobs to SpongeBobs, whatever, So this theorem tells you that if you have a rigid motion on a finite dimensional inner product space over the reals, then there exists a unique orthogonal operator T, and translation, I think we talked about in here before at some point. We just take the input and add a vector. That's just a translation. It's not a linear transformation, right? Translation is technically something, it's not a linear transformation, because if you're translating by a non-zero vector, what's T of 0 go to? Like if we're translating by the vector P, T of 0 is equal to P, which is of course not equal to 0, so it's not a linear transformation, but translation is nevertheless pretty simple. And it turns out that any rigid motion can be written as the composite of a translation and an orthogonal transformation. Notice that there's no assumption of linearity in this definition. So in this theorem, we're saying that preservation of distance implies linearity. That's not easy to prove. So I'll just say that. But I like to prove that in abstract algebra. I think that's the right place for that to be proved, not here. So this gives you a complete catalog of orthogonal operators in the plane. There are two kinds. There's either rotations or reflections. That's all you got. And it's a rotation if the determinant is 1. It's a reflection about some line through the origin if the determinant is -1. That's it. This proof is not clever. I'm not saying that's not the right thing to say. It's easy to follow. I stand by my words. So you can look at that. So corollary, any rigid motion of the plane is going to be a rotation followed by a translation, or a reflection about a line followed by a translation, because those are the only kind of orthogonal transformations, either rotations or reflections. That's the basis for like a lot of this two-dimensional art stuff you see about like tessellations and things. If you want to maintain shapes, you can only use reflections or rotations in translations. Yeah. So we should talk about this once I put this away. Conic sections are a super nice application of all this stuff. If a conic section is basically defined by a quadratic form equal to a constant, and since the matrix is symmetric, that means that we can orthonormally diagonalize it. So I'm going to show you some examples of that in just a second. That's in this section. There's a couple of examples. I didn't give you any problems from the book because I have good problems already. Why reinvent the wheel. Finally, if we have the last thing here, section 6.6, I really just want to state a theorem for you. I have a homework problem in your mission 6 which will help you understand the theorem better. All right, just an example really. So there's the concept of an orthogonal projection. If you have a linear transformation from vector space to itself, be a projection. So what does that mean? That means that t squared is equal to t, I believe, was our previous definition of projection. Well, t is an orthogonal projection if the perp to the range is the kernel and the perp to the kernel is the range. And so here's the theorem that characterizes these. If you have an inner product space linear transformation, then t is an orthogonal projection if and only if t has an adjoint and t squared is equal to t star. So it's self-adjoint and it's equal to its square. This is an infinite dimensional theorem. How do I know that? Logically, can you guys tell me why this must be an infinite dimensional theorem? Let me ask a question a different way. Would I need to assume that t has an adjoint if we were in finite dimensions? No, we proved that the adjoint of a linear transformation on a finite dimensional inner product space exists, right? Because there exists that vector y that we can define t star of x to be equal to the y, remember? That whole construction. By the way, the y in that construction that we did, you know what I'm talking about? Do you guys know what I'm talking about when I say y? So like in the construction of the adjoint, there's a vector y that appears in the proof. That is what's known as the Riesz vector. I mentioned the Riesz vector somewhere in the, I don't have a copy of it. You guys have a copy of it. So last but not least, the spectral theorem. So this is really the last thing I want to tell you guys from the book, I think. We're going to shift over to my notes past this point, all right? So, but this is the spectral theorem. If we have a linear operator on a finite dimensional inner product space, and you've got distinct eigenvalues 1 through k, we're going to assume t is normal if we're over the complexes. We're going to assume t is self-adjoint if we're over the reals, right? And w sub I is the ith eigenspace. Ti is the orthogonal projection of v onto wi. If that's the case, then v is the direct sum of your eigenspaces. The perp to the ith space is the sum of all the other ones, right? So like it's just like what you want to think intuitively, and they commute or they square to themselves. That's what this says. Ti is equal to tj. Excuse me. Tij is equal to tj if I is not equal to j, right? Because they're both equal to 0. So not only do they commute, they multiply to 0. You can write the identity as a sum of the t's, and t itself can be written in terms of an eigenvalue weighted sum of projections. I'm personally very fond of this theorem because it's how I make examples. Suppose you want to make a matrix which has eigenbasis such and so forth, all right? Well, what you do is you take that basis and you build the projections, all right? You build the projections with the basis, and then you just simply multiply those matrices by whatever numbers you want to appear here, like, I don't know, 47, and then you've got a matrix with eigenvalue 47, which has the eigenbasis which you use to construct it. And if you make your basis not dumb, if it's somewhat complicated, it can make pretty ugly looking examples. The trick is doing this in such a way that you don't get like square roots all over the place, which is hard. So anyway, now you know my secrets. So yeah. Let me shift over here. So I will post these for you guys, but this is my, chapter 10 is where we're going to be And I think we're going to really start in section 10.3. Like 10.1 and 10.2 are like isomorphism theorem, cosets, dual spaces. That might be helpful to you guys just to have something different to review. I'm going back a little bit further to show you I've got examples of quadratic forms in here. So I said I was going to write things. I guess I lied. I'm sorry. So this I will post shortly, but a quadratic form is a function from Rn to R whose formula can be written in the form like the vector transpose A times X for all X in Rn. And we're going to insist that the matrix of the transformation of the quadratic form be symmetric. Why? Because then we have the real spectral theorem. We know that it's orthonormally diagonalizable. Hooray. So like, for example, if I have A, B, B, C, if I multiply this out, it gives me something of the form like ax squared plus 2bxy plus y squared. The three-dimensional case, it's like this. So the reason these are called quadratic forms, it should be somewhat self-evident, right? Every term in the expression is quadratic order, right? That's why it's called a quadratic form. All right, so show you some examples here. Well, first of all, some really stupid examples. If we have x squared plus y squared and we look at z equal to x squared plus y squared, that gives us a paraboloid, right? A paraboloid. And the level curves of this are just concentric circles in the plane, right? So remember Calc 3, we can either look at things in terms of their graph or their level curves. So the graph is a paraboloid, the level curves are circles for this one. If we have the quadratic form x squared minus 2y squared, you get a hyperboloid, right? This time the level curves are hyperbolas and the graph is, well, it's a hyperboloid, right? So the origin here is neither a min nor a max, it's a saddle point. You can also have something like 3x squared, then you get a trough, a parabolic trough. The origin is neither, it's I don't know what it is. It's a, I guess it's still a saddle point. Is that I don't know, is that a minimum? I guess it's a minimum, but I'm not happy about it though. All right. Three-dimensionally, much harder to draw the graph, right? You want to graph w equals, x squared plus 2y squared plus 3z squared, well, go to it. But I'm just going to draw the graph. I'm just going to graph the level surfaces. The level surfaces of this quadratic form in 3-variable are, well, they're ellipsoids, right? So you get this family of ellipsoids that, foliates R3. So here's the big theorem. If you have a quadratic form, then you can change to eigencoordinates, right? You can transform by using the eigenbasis for A, V1 through Vn. And when you do that, this P transpose AP is a diagonal matrix of the eigenvalues. And so if P transpose X is the y vector, the eigencoordinate, then the formula for the quadratic form simply becomes an eigenvalue weighted sum of squares. Which is beautiful because that means that any ugly example can be put back into the form that I just showed you the nice graphs of. Like this one, 2x squared plus 2xy plus y squared. Well, I don't know what that is if I set it equal to k, but if I look at this, I find the eigenvalues are 1 and 3. I can tell you right now that q of the eigencoordinates is equal to, y1 squared plus 3y2 squared, because the eigenvalues are 1 and 3. So it's a sum of squares, both positive. First eigencoordinate squared plus 3 times the second eigencoordinate squared. I don't even need to find the basis to tell you that that's the formula. But here's the basis. This and this are my eigenvectors, and if here's the eigencoordinates. I used x bar and y bar rather than y1 and y2, my bad. So, just a different notation. But anyway, here is the formula for the quadratic form in the eigencoordinates. Now, if I set this equal to a constant, it's obvious that we're looking at an ellipse, right? I don't think it was obvious back here. If I set this equal to 1, equal to a constant, is it obvious that's an ellipse? It's not obvious to me. But in the eigencoordinates, it becomes clear that it's an ellipse. That's the beauty of diagonalization, is it takes complicated things and makes them simple. To give you another example, well, this one's kind of dumb. This one, I don't think we need linear algebra for this, honestly, guys. That's x plus y squared, so duh. It's a parabolic trough that's been like rotated. Anyway, I don't care about that example, whatever. 4xy. So if you set that equal to a constant, if you go through the find the eigenvalues, plus and minus 2, if you change to the we work through slog through the details here, you can change the formula to minus 2x bar squared plus 2y bar squared. So if I set that equal to a constant, that's a hyperbola, right? Which is why we tell pre-calculus students, if you have like the reciprocal function, which is like y over x, y is equal to 1 over x. Well, think about that. That would be the same as xy equals to 1. It's a close cousin to this example. That's a hyperbola, but it's been rotated 45 degrees, just like this one. So to really do pre-calculus, you need linear algebra, truthfully. Truth be told. Here's another one. Let's see if I got a picture. Well, there, it's a tilted ellipsoid. So anyway, I just wanted to show you guys some of that. I gave you a couple of token homework problems. I think if you have trouble with those, just let me know. I know I haven't done too much in class. Yep.
What do complex eigenvalues do to quadratic forms?
Oh, well, they don't exist for quadratic forms because we're talking about a real quadratic form, so the matrix is symmetric. And